A farmer has 150 acres of land and a strict limit on days spent trimming and picking crops. The goal is maximizing profit. In operations research, we translate physical limits like land and labor hours into strict mathematical equations. Plotted on a graph, these equations become rigid, intersecting walls. The enclosed space they create is called the feasible region. Every coordinate inside this boundary represents a valid, survivable farming plan. This chart shows the feasible region for our farm, bounded by polygon A, B, C, D, E. The red ISO profit line represents total cash, sweeping outward as profit increases. Maximum profit occurs exactly as this line exits at vertex B, 60 acres of A, 90 of B. Looking at this table of corner point calculations, we can verify the math. Vertex B yields $29,550, the highest cash value on the board. Finding that mathematical peak gives us a perfect strategy for a static moment in time, but reality fluctuates. To see if this plan survives contact with the real world, we have to stress test the geometry using sensitivity analysis. The first layer of volatility is the market. Crop prices fluctuate daily. If the profit for crop A increases from $140 to $200 per acre, the mathematical slope of our objective changes. Watch the ISO profit line. As the price shifts, the line rotates. It tilts, but its outermost anchor remains locked on point B. The physical strategy, planting 60 acres of A and 90 of B, stays exactly the same. Only the final cash deposit increases. Let's create a tipping point. Crop A spikes to $300 an acre, and crop B drops to $200. The red line pivots sharply. Point B is no longer the outermost peak. It now exits at point C. Our plan shifts to 75 acres of each. Changing market prices rotates the objective function. You do not need to change your operation unless that line tilts past the slope of the walls holding it in. Let's move from market prices to the physical constraints of the land itself. Suppose poor soil conditions mean the farmer can safely plant a maximum of 80 acres of crop A. We map this by dropping a rigid boundary at the 80-acre mark. A portion of our feasible region is completely sliced away. The possibility space is now smaller. But look at our optimal strategy at point B. It sits safely inside the new boundary. This is a non-binding constraint. It permanently alters what is physically possible. But because it doesn't touch the outermost vertex, it is mathematically irrelevant to our current optimal strategy. Now, let's apply a much more aggressive external force, a strict government cap on total pesticide use. A baseline limit of 1,000 liters maps neatly onto our space, hovering above the polygon without restricting it. Then they tighten the regulation to 800 liters. The wall pushes inward, slicing off the top right corner. Both point B and point C are completely erased. The optimal strategy we calculated earlier is now physically impossible to execute under the new laws. Tightening resources translates the geometric walls inward. You are forced to adopt a radical new strategy the exact moment a physical boundary consumes your optimal vertex. This exposes a harsh reality about optimization. Finding the highest point mathematically is the easy part. Defending that point against a chaotic world is the actual challenge. Look at this dense list of scenarios facing our 150-acre farm. Changing crop yields, environmental regulations, pesticide limits. Each of these text scenarios represents an invisible geometric pressure waiting to warp the polygon. Sensitivity analysis is the process of mapping these invisible thresholds. It calculates exactly how much external pressure a plan can endure before the geometry shatters. Up to this point, we've only mapped two variables, crop A and crop B. Real industry problems do not operate on two variables. They require balancing dozens, hundreds, or thousands of inputs simultaneously. Take this production matrix for a perfume company. They need to balance 4 different product lines against 3 distinct raw materials. Adding a third variable extrudes our flat 2D polygon into a 3D shape. The optimal strategy still sits at the highest vertex. Scaling to 100 variables creates identical, multi-dimensional structures, even if human brains cannot visualize them. Computer algorithms, like the simplex method, navigate these invisible hyperspaces using the same logic. They crawl along the edges until finding the outermost peak. Linear programming trains us to view operations as physical space. It builds geometric intuition for how complex multivariable systems adapt to a volatile world.